Hi everyone, welcome to this machine learning and MFG game webinar. So today we're very glad to have Batuhan Yardim, who is a PhD student at ETH Zurich with Niaohe. And so today Batu is going to present on one is mean field reinforcement learning, tractable and relevant. So thanks a lot, Batu, and you can start whenever you're ready.
Sure. Thank you very much, first of all, for the opportunity and the invitation. I'm glad to be presenting here. So yeah, I'm Batu, and today I'll be talking about our recent work on trying to answer the question, when is mean field RL tractable and relevant? Just a quick check, I guess my voice is fine.
Yeah, it's good.
Okay then, so this is joint work with Arthur Goldman, who was an intern at ETH last summer, and also my PhD advisor, Professor Niaohe. And I'll be talking about some results that are going to appear in AMAS 2024, alongside some recent improvements and additions. So with that, I can start. The main, I guess, framework we'll be talking about is that of reinforcement learning. And what is RL in a nutshell? Basically, it's let's say the objective of making good decisions in some sense by learning from experiences in uncertain environments. So to make that more concrete, for example, typical single agent RL setting, we would like to learn a policy pi that maps the current environment state to some distribution over actions. We would like to deploy this to an environment model, which consists of a transition dynamics model P and rewards model R, which are often unknown, but have to be inferred from data. And we would like to optimize a value function, which is typically the, let's say, the discounted infinite horizon cumulative reward function. So with that, RL is essentially a certain optimization problem with some structure. But of course, one of the main strengths of RL is that it is not restricted to single agent setting, but rather can be applied on much more general n-agent or multi-agent settings. And in this case, when we generalize to n-agents, let's say, if the game or problem is competitive, the natural objective is not just function maximization, but rather finding a certain equilibrium policy for each agent, for example, a Nash equilibrium. But it turns out this is, in some sense, difficult, even for finitely many agents. And for that reason, so the main reason of this is essentially the curse of many agents, especially when n is very large. The search space can grow exponentially fast, which makes the problem challenging. But for that reason, there has been a lot of research on finding these islands of tractability, essentially games which have a bit more structure and are relevant to the real world and still yield tractable formulations. For example, in between the n-agent setting and the single agent setting, the zero-sum two-agent setting yielding a min-max optimization problem tends to be tractable. Or, for example, there has been research on Markov potential games, which are games with a certain potential function structure. So mean field games, from the perspective of multi-agent RL, is essentially one such, let's say, tractable formulation when the number of agents is very large and the game exhibits certain symmetries. So namely, if we have n agents where n is large, and if the dynamics and rewards, let's say Pn and Rn of each agent are equal and kind of homogenized over all agents, we can take the n goes to infinity limit to formulate a certain abstract game called mean field game, which is in some sense a much lower dimension problem because we would like to learn for a single representative agent playing against the distribution mu, which I'll formalize in a bit. But the nice thing is that there are, of course, guarantees on when the solutions on the right perform well, essentially on the left, where we have finitely many agents. Of course, as you probably know, this is a very widely popular framework, even beyond RL. has been introduced in around 2006 independently by two seminal papers. It has been already studied in game theory, stochastic control, applied probability, and so on, and has many applications, for example, in traffic, epidemiology control, resource management, and so on. So with this brief overview, I can formalize the setting a bit more. Namely, I'll first define the n-agent setting mathematically. So what do we mean by the n-player, let's say, symmetric game? So the game consists of n agents indexed with I from 1 to n. We assume we're given a finite state action space, SNA, and a horizon, which can be a natural number or infinity as well. And for every time h, I defined empirical state distribution mu hat h as essentially the distribution of the random variables of states of each agent over state space. So the actual realized empirical distribution. And the game dynamics are then defined as follows here. Namely, the initial states of each player are sampled from mu0 independently. And at each time step, the next state evolves according to the state of agent I, action of agent I, and the empirical distribution of the rest of the population. And likewise for the rewards. So essentially the interactions between agents are only allowed to happen through this empirical distribution mu hat, which is why agents are, in a sense, homogenized in the game dynamics. And with this definition, the objective we would like to optimize over is the so-called exploitability. So namely, we define epsilon Nash equilibrium as a case where no single agent can single-handedly improve their expected return by deviating from the equilibrium unilaterally. So if the expected improvement they can get by deviating is upper bounded by epsilon, we call strategy profile epsilon Nash equilibrium. And if it's 0, it's called just a Nash equilibrium. And we can also more clearly define what these JIs are. Namely, in the infinite horizon setting, we have a discounted cumulative rewards defined here. We assume gamma is less than 1, so that everything is clearly defined and rewards are bounded. And similarly, in the finite horizon setting, we simply just sum up the rewards over the entire time horizon. So the definition here clearly defines an n-player game, but as I said, it's intractable. So this brings us to the nicer mean field game formulation at the n goes to infinity limit. So I'll be talking about two formulations. The first one called the stationary mean field game. Here we assume there's a fixed population distribution mu, which essentially induces a MDP. So we assume that there's a single representative agent whose initial state is sampled according to mu, and following state and actions are evolving according to the policy of the agent, and where we plug in the mu into the dynamics function P. And likewise, dependence of the rewards on the population is fixed in its population argument. And we define the value function for a certain policy pi as discounted sum of these rewards, where the population is fixed to be mu. And in this setting, the solution concept we'll consider is that of a stationary mean field game. Namely, we're looking for a pair of policy and population distribution, pi star, mu star, which should satisfy the optimality condition, so that the policy pi star is optimal with respect to the population. And secondly, the population distribution mu star should be stabilized under pi star. So here I wrote essentially the marginalized probability distribution of the next state if we start from a certain distribution mu star. This operation will turn out to be important for later analysis. So I'll define this as the population operator gamma p for a given population distribution mu star and policy pi star. So the second closely related solution concept or mean field game concept is the so-called finite horizon mean field game. In this case, we have only finitely many time steps. So we are interested in a not necessarily stationary population distribution mu for h equals 0 to h minus 1. In this case, the dynamics of the representative agents also evolve according to the fixed population distribution, though with this additional time dependence. And we would like to consider the value function v defined here, that is the sum of expected rewards over time. And in this case, the solution concept is also very somewhat close in spirit. So we would like to find a policy pi star that is optimal with respect to the induced population flow that is defined here as mu superscript pi star. In this case, since mu is not stationary over time, we define the induced population flow as repeated applications of gamma p to the fixed mu0. So these two solution concepts define as abstract somehow problem that is not immediately tied to a concrete, let's say, competitive game, but somehow the definition suggests a connection, which turns out to be mathematically established. So if we solve this game, if we solve these optimization problems, we can get approximate solutions to the more concrete n-player game that I introduced earlier. So to present this more rigorously, there are really two main desired properties of mean field RL. The first one is, since it's an approximation, we hope that mean field games are good approximations of the n-player game. So that is, we hope that if we have a solution to the mean field game, if we deploy it to the n-player game, we should get a sufficiently good exploitability. And this has been rigorously established in many settings. In the discrete time, that we know that for PNR that satisfy continuity conditions and several other technical details, the exploitability is actually guaranteed to converge to 0 as n goes to infinity. And in much richer literature of stochastic differential mean field games, there are also many bounds, and in fact we know their optimal rates with respect to number of agents, but this is somehow a different setting from what I'll be talking about now. And coming to the second desired property that we would like to have from the mean field game formulation is that of tractability. Since we construct the mean field game as an approximation to the n-player game, ideally we would like to have this formulation easier to solve than the n-player game. So there, in the literature, to the best of our knowledge, no clear characterizations of this, but there are many works that establish tractability in special cases. For example, in the stationary mean field game setting, if you have sufficient regularization and a contraction assumption, algorithms such as Q-learning, policy gradient methods, fictitious play, and so on, can be shown to converge to solutions. Though it is known that apart from trivial cases, contraction, at least without regularization, is not possible in general. Likewise for finite horizon mean field games, this time under a montonicity assumption, algorithms such as fictitious play, online mirror descent, and policy mirror descent have been shown to work well. But in both cases, there's no characterization of when the game can be, when we can hope the second desired property of tractability to hold. So these two desired properties brought us to ask a few questions on both sides. Firstly, from the approximation side, we would like to understand how large n must be fundamentally for a good approximation of the true game. So we say fundamentally because we would like to both have a good upper bound on exploitability or our approximation error, but we also would like to understand what might go wrong. So if there are any fundamental lower bounds on the approximation error. And secondly, on the approximation side, we would like to ask which we think is an understudied question, at least in the discrete time case. How robust is the approximation error to violations of symmetry? So in many real-world applications, maybe symmetry doesn't hold exactly, but it's a very reasonable assumption that holds on average. So we will like to understand the sensitivity to such violations. And on the tractability side, the questions we would like to consider is, firstly, when is it computationally tractable to solve mean field games? So we mean this in a sense that when can we hope to have polynomial time algorithms for solutions? And secondly, if this is not possible, how does the computational complexity at least relate to the n-agent the n-agent formulation? So if it's actually easier than the n-agent setting, we would like to study this. So with that, I'll quickly go over the standing assumptions. We'll only consider finite state action spaces, though some results might naturally generalize to more richer spaces. And secondly, we'll only consider Lipschitz dynamics and rewards. By Lipschitz, we mean for any fixed state action pairs, R and P is a function of mu here, must be Lipschitz with respect to the L1 norm. So the choice of norm doesn't matter too much here because of the space being finite dimension. This assumption is actually standard in many works. It has been considered thoroughly in RL, multi-agent RL literature. And also, since we're interested in some hardness and lower bound results, these results naturally generalize to the more general case of continuous PNR. So we can move to the main results, but I'd just like to ask if there are any unclear points or any questions from the audience.
Maybe one quick question. Sorry,
Yeah,
when
sure.
you talk about the hardness of solving an agent multi-RL problem, you mean computing a Nash equilibrium in the multi-agent game? I mean, in the finite layer game? Or computing an approximate equilibrium?
So computing an approximate.
Okay.
So computing the exact Nash equilibrium, so I'll talk a bit more about this, but computing it exactly might just be impossible in any computational model because the solution might be irrational, for example. So we kind of relaxed a bit to say up to arbitrary accuracy.
Accuracy. Okay, and then the same question for mean field game, for example,
Exactly.
and you want to compare the difficulty. Okay, thanks.
Yeah, sure. So I guess I can move on to the first set of results on the approximation side. So as I said, the question we would like to answer is how good is the MFG solution to the n-agent game? Of course, the metric of goodness in this case is the n-agent exploitability, where we take the mean field game solution and pi star MFG and deploy it on the n-agent game. We measure the exploitability of each agent, and we would like the upper bounds. So actually, there have been many works in discrete time setting here. So this 2008 paper by Naji Salde and et al. Essentially considers a much general setting, but the results can be generalized, for example, for stationary mean field games, for continuous PNR, to show that the exploitability asymptotically goes to zero. So we can't come up with the explicit upper bound on how fast it goes, but we know that if n is large enough, the exploitability always goes to zero, which is a encouraging result. In fact, just assuming continuity of PNR, this is probably the best we can get. We can't explicitly upper bound the approximation error. But assuming Lipschitz dynamics and rewards, we can actually come up with the explicit upper bound by somewhat following the same analysis, but refining in certain ways. So we did this, and for finite horizon mean field games, we came up with this upper bound, where the approximation error goes to zero, the function of 1 over square root of n. But the dependence on the time horizon h might be, in the worst case, exponential. So clarify, L here is the Lipschitz modulus of the population update operator, which I introduced earlier. And if L is larger than 1, this upper bound might just be exponentially growing in H and might become vacuous very quickly for even moderate H. And likewise for the stationary mean field game case, assuming that the population update operator is non-expansive, we can get a similar 1 over squared of n rate in terms of the number of agents n, and this time with a nice cubic dependence on the effective horizon 1 minus gamma. But the 1 over squared of n rates doesn't hold in general if gamma p is allowed to be expansive. So these two questions suggested, these two results suggested the question, if gamma p is in general allowed to be expansive, is it really fundamentally the case that we have a exponentially growing exploitability lower bound? So we studied this question, and we firstly came up with the explicit lower bound for the finite horizon mean field game. That is, we showed that there are certain, even actually simple mean field games, where the game with horizon H has a unique Nash equilibrium pi star H. And if we deploy it to the n-player game, as I noted here, we get constant time average exploitability unless the number of agents is exponentially growing in the time horizon. So the main takeaway, while being somewhat expected, is that even for Lipschitz dynamics and rewards, the approximation can be very bad even for moderate H. And intuitively, the reason for this, as expected, is the fact that the n-agent system can exhibit chaotic behavior. And one interesting detail here is if P doesn't depend on mu, which is a common assumption, for example, in finite horizon mean field games from a computational perspective, this issue will go away. So the approximation rate will be polynomial. And in fact, the number 2 is not special here. In general, for L Lipschitz dynamics, we can show an exploitability of L to the power H being suffered. So this somewhat tightly characterizes the approximation speed in terms of the horizon for mean field games, for finite horizon mean field games. And moving on to the stationary case, we likewise can show that there are simple stationary mean field games that have a unique solution, let's say mu star and pi star, such that when deployed on the n-player game, the mean field solution suffers from exploitability n to the power log gamma, essentially. So to kind of clarify this a bit, even for a relatively popular effective horizon of 0.99, this lower bound yields n to the power minus 0.015, so it's much slower than 1 over squared of 5. The main takeaway being here that without assuming non-expansiveness of the population operator, the convergence in terms of number of agents can be even prohibitively slow. So these sets of results answer the question, convergence in terms of number of agents. The next question I mentioned was how robust is the mean field game solution to violations of exact symmetry? So the motivation of asking this question is the fact that in the real world, exact symmetry might rarely hold due to heterogeneity, imperfections, or minor asymmetries between agents' capabilities. I can note that there are some already extensions, such as graph-form mean field games and multi-population mean field games, that kind of break this symmetry. But these two formulations essentially still assume some form of, let's say, meta-symmetry, and they're in fact both reducible to a certain mean field game given the, for example, graph-form formulation. So they don't really, they still assume some form of strict symmetry, which brings us to the question, how can one quantify proximal symmetry in this setting? So coming back to this original picture from a few slides ago, where we had the multi-agent RL formulation and infinite player limit. So now, instead of assuming all PNs and RNs, so all dynamics and rewards being exactly equal, we will, in some sense, to be clarified, assume that they're just close, but not necessarily equal. So to be more clear, in the finite agent setting, if you don't have exact symmetry, the dynamics of each agent, of an agent I can be expressed as a function over the current state and action of the ith player and the state and action tuples of the rest of the population, so of the rest of the n-1 agents. And likewise for the rewards Ri. So with these rewards and dynamics, we can clearly define value functions and exploitability, just as before. But now we would like to approximate this potentially asymmetric game by P that depends on the state and action of the current agent, but kind of homogenizes the rest of the population. So now just looks as distributions over state and actions rather than n-1 tuples. And likewise for the reward function. So given these definitions, we can define a concept of, let's say, alpha-beta symmetric game, where we say a game is alpha-beta symmetric if the deviation from the P, idealized, let's say, mean field game P, over all population and state and action configurations is upper bounded by alpha, and the deviation of rewards from the idealized mean field game reward function is upper bounded by beta. So it'll be clearer why we define alpha and beta separately here, but we would like to understand the sensitivity of the mean field game solution to alpha and beta. So here, the upper bound we have is actually a positive result that suggests that the mean field game formulation is actually robust to alpha and beta. Namely, we show that when we solve the idealized mean field game and deploy it to the approximately symmetric n-player game, we suffer from an exploitability that scales as before with 1/squared of n, but with a non-vanishing depends on alpha and beta, but something which recovers the original result if alpha and beta are equal to 0. So the main takeaway here is we have robustness towards approximate symmetry, but in different ways. For example, asymmetries in dynamics are much less correlated, especially since there's this exponential dependence on time horizon, whereas we have a much nicer polynomial dependence on asymmetries in the reward functions. So yeah, these results basically gave our answers towards the approximation side of things. Before moving on to the tractability side, I guess I can also ask if anyone has questions, if there are unclear points.
I do have one. Hi. For the last result you show regarding alpha beta symmetry, this was for the finite horizon case, I guess.
Yeah.
And do you have a similar result for a stationary MFG, or are things different, or no result?
I don't have it here, but actually we do have something similar that looks kind of as expected. We would have a non-vanishing term in alpha and beta as before, but once again, so essentially we can almost replace the horizon H with the effective horizon 1 minus go, almost.
Okay, so you don't have a worse dependency on alpha beta depending on I mean, two kind of MFGs have the same kind of dependency on alpha beta with respect to the quantity that makes sense in each case.
Exactly. Yeah.
Thank you.
Thank you.
Yes. Can I ask a question?
Yeah, sure.
Yes, thank you. I'm very interested in this notion of symmetry that you talked about. I have a question from standard mean field game. Like when you have this symmetry, it implies that all agents are negligible in some sense. Now that you're allowing for some bound to go away from symmetry, do you see in computations that there is some agent that are not negligible in some sense? Like, do you see something like that or not?
Yeah, actually, that's a very interesting question. So here I presented the results kind of starting from mean field gain, and then assuming that the PIs explicitly approximate well the idealized mean field gain P, for example. But there's also another way to look at it, assuming that we're just given these functions PI without any mean field gain formulation. In that case, if we would like to formulate a meaningful, we would like to construct a meaningful P, then just as you said, we need an additional assumption of something like bounded variation or like a negligibility of each agent, because otherwise the mean field gain limit is not meaningful. So in a sense, but just by assuming this alpha beta symmetry here to some idealized mean field gain, we already implicitly assume some negligibility of agents. So
Thank you.
This is like clear.
Thank you.
Yeah, no worries.
There is another question in the chat. Sorry to interrupt. So someone is asking if only a constant number of the agents deviate from the average policy, can we obtain a better result that decays with a number of agents n?
So maybe I can. So I guess.
I guess if there is only a constant number of agents deviating, then they will become negligible in the limit, but I don't know what's your take on that.
That's an interesting question. I guess so part of it might be related to the definition of Nash equilibrium. So in Nash equilibrium, we always assume unilateral deviation. But maybe there's a stronger notion that considers multiple agents deviating. So that might be related to that. In terms of just the mean field flow, it doesn't matter how many agents deviate. In the infinite agent limit, they will be negligible, I guess. So if 10 agents deviate and we take n to infinity, it won't matter. From the perspective of optimality, I'm not so sure. Maybe. Great.
Okay, thanks. Maybe one more question, Zeta. You have a question?
Yeah, hello. I also have the question about symmetry. Let's assume that the agents in this group, they have the interaction reward function as a mean field gain, but they also have the very independent individual reward. So can they be regarded as a case of the asymmetry?
Yeah, exactly. So as I said, we can look at this result from the converse, the inverse perspective, and say that maybe it's not even a mean field game to start with. Just agents have different objectives, different reward functions. But then, as I said, I think for the mean field approximation to be meaningful, we need to impose some additional constraints on the RIs. So it's not the case, I think, that the rewards can vary freely, in a sense.
I see. Gotcha. Thank you.
Okay, no worries.
Okay, thanks. So maybe we can continue, and if there are more questions, we can ask later.
Yeah, sure. So yeah, I can continue with the tractability results. So as I said, the question we're tackling here is it computationally easier to solve MFGs compared to n-agent games in the general case? So just a quick presentation of what has been done in literature and our results. So there are many positive answers here for stationary and finite horizon mean field games. For example, in the stationary case, as I said, with regularization and with some contracted population dynamics, one can show that the problem reduces to log epsilon -1 iterations of single agent RL. So essentially, if we repeat single agent RL, any single agent RL algorithm logarithmically many times, we get a good approximation of the mean field gain Nash. Likewise, for the finite horizon setting, there are many continuous time analysis, but a recent finite time analysis shows that if we have monotone rewards and mu independent transition dynamics P, we can reduce the mean field gain problem to epsilon to the power -2 policy evaluation. So policy evaluations here being, for example, an application of TD learning or any approximation algorithm for the Q values of a given policy. So these two cases are nice, but it wasn't clear to us if, in the absence of these key assumptions, the problem still remains difficult. For this, we established a sequence of hardness results in the sense of showing that some of these problems are PPAD complete. So I'll elaborate more on this, but we show that in the stationary mean field game setting, Lipschitz PNR assumptions lead to essentially hard problem. Likewise, in the finite horizon setting, even if P is allowed to be independent from mu, even linear rewards lead to PPAD complete formulations. So as I kind of intuitively to present it, PPAD complete will mean that problems are likely to be intractable in general. So I'll try to make these results a bit clearer. First of all, what do we mean by computational complexity? What we don't consider here is any statistical error. So we assume that the mean field game dynamics are known exactly or given to us without any noise. So we know the functions P and R exactly. And of course, our measure of accuracy in the setting is the mean field exploitability. So the exploitability of the policy pi star with respect to the population distribution it induces. So to clearly define the computational problem, it is the problem of given the horizon or effective horizon, state space, accurate space, and exact descriptions of PNR, and a desired accuracy epsilon, the problem of finding pi star such that the exploitability is upper bounded by epsilon. So this is the computational problem we will analyze. And a minor detail here is the fact that if you would like to talk about computational complexity, we need to represent the functions PNR somehow. And representing functions in general, or representing even Lipschitz functions in general, is a difficult, potentially difficult task. So we restrict our attention to a subclass of Lipschitz dynamics and rewards, which I define here. So we call these simple dynamics and rewards, and they're PNR, which are only allowed to depend on components of mu and several constants in terms of the operations, addition, multiplication, division, subtraction, and max and min operations. So essentially, we assume that PNR are given to us as a computational graph in terms of these operations. So likewise, in an even more restrictive setting, we can have PNR to be linear in the mu components for any state action tuples. So I denote these classes as PSIM, RSIM, PLIN, RLIN. And one thing to note here is, since these are subsets of general Lipschitz continuous functions, the difficulty results will also apply to PNR. So in a sense, by assuming this, we prove a stronger statement of hardness, of computational hardness. And our results will be in terms of the complexity class PPAD. So as a brief introduction, PPAD, standing for polynomial parity arguments on directed graphs, is a complexity class introduced in the seminal paper by Christos Papadimitriou in 1994. It's a total function problem, meaning that the problem is of computing a relation between two sets. For example, given a game, find the Nash equilibrium, and so on. It is conjectured to have no polynomial time solution, but it's included in NP. So looking at the graph on the right, it's somewhere in between NP and P. And following computational complexity language, we call the most difficult problems in PPAD as PPAD complete. So they're the most representative problems in this class. And to give some examples, typically considered in literature, for example, finding the Nash equilibrium of an n-player general sum normal form game is PPAD complete. Finding the approximate fixed point of a continuous map is PPAD complete, finding a free-colored triangle in Sperner's lemma, and also some forms of coarse-correlated equilibria concepts in stochastic games are also PPAD complete. So it's essentially an important class for especially game theory. And one thing that puts all these problems in the same class is that they're all problems that we can mathematically prove to have solutions. For example, we can prove that natural equilibrium always exists. And the mathematical proof follows a parity argument, which gives the name of the class. So concretely, for example, I'll talk a bit about the problem of finding an epsilon fixed point of a continuous map on a cube. So the problem of finding an epsilon fixed point, x, in terms of any norm, where we're given a description of a function on the d-dimensional cube, let's say in terms of arithmetic circuit or Boolean circuit, is PPAD complete. So there's no explicit lower bound on how difficult this problem is, but one argument that motivates the hardness of this class is if we don't have a description of f, but we can query values of f through an oracle, there are no exponential lower bounds for this problem. So this kind of motivates that we might need exponentially many iterations for solving PPAD complete problems. So with this brief overview of PPAD, I can start presenting the results. So firstly, for stationary mean field games, we show that even ignoring optimality, finding a stationary distribution mu for the solution can be PPAD complete. So as a reminder, the solution concept in stationary mean field games was a pair of policy pi star and mu star, where mu star is stabilized under pi star. And it turns out even finding this mu star, even if we know the optimal policy pi star, is PPAD complete. This is shown by constructing an equivalence to generalized circuits. And it somehow motivates the common assumption in the literature that the population update operator is contracted, or in some norm or semi-norm, it's non-expansive. Because in that special case, the problem is no longer PPAD complete. And likewise, for finite horizon mean field games, we show that even for simple rewards or linear rewards, even if P is independent from the population distribution mu, and for a fixed horizon of 2, the problem is in general PPAD complete, showing that even with relatively strong structure, the mean field game formulation in finite horizon might be hard to solve. One important maybe detail aside here is that of pseudo-polynomial algorithms. So of course, in the language of complexity, polynomial time algorithm might be too strong of a wish, because in optimization language, this translates to linear convergence, because epsilon can be described in logarithmically many bits. So a natural question is it possible to have polynomial time solutions in all parameters except epsilon? But this is turned out likely to be not the case, because when we modify the computational problem to return the answer for some fixed epsilon 0 rather than an input argument epsilon, the PPAD completeness holds. So in a sense, pseudo-polynomial time algorithms are likely to be non-existent as well. So those are all the results that I would like to talk about as a kind of general overview of questions I asked in the first few slides. So on the approximation side, the question, how large must n be fundamentally for a good approximation of the true game? The answer was potentially exponentially large, at least in the general case. At least if you don't have additional structural assumptions. And second question, how robust is approximation to violations of symmetry, was actually answered positively by the concept of alpha-beta symmetry. So the mean field game formulation can tolerate minor deviations from perfect symmetry. But for the tractability side, the question if we can have polynomial time algorithms is likely to be answered negatively unless PPAD is equal to P, which is believed to be not the case, because we show that these formulations are PPAD complete, essentially the most difficult problems in the class PPAD. And the question of the relation between the complexity of the n-agent setting and the mean-field game setting is answered by, in general, they're equivalent. So from a complexity theory perspective, they have the same complexity. But one thing maybe to note here is that these questions we asked might still not rule out, and they obviously don't rule out the effectiveness of mean-field games in many settings. For example, in the most a typical application of mean-field games in economics, where we have a very large number of agents already, maybe like hundreds of millions of agents, which might let us tolerate even this exponential dependence in time horizon. And it's likely not to be the case that we will need to deploy RL, rather their economic hypothesis, like the efficient market hypothesis, which suggests that the population in aggregate is close to a Nash equilibrium. Likewise, it's not a game, but in some even larger systems, for example, interacting particle systems, the number of particles can be orders of magnitude larger, allowing us to tolerate an even larger time horizon. And besides, there's no notion of optimality that can be considered. It's just particles obeying a physical system. So the conclusions we draw here really apply only to the case where we're given an agent system and we would like to quickly or efficiently come up with a solution using mean-field RL. So it's somewhat at the intersection of mean-field games and RL. And finally, I think one interesting conclusion of the work is that firstly, the assumptions that were proposed in past work for analysis of mean-field games can be actually justified by our harmless results. And also interestingly, some assumptions that were considered for good tractability turns out are also necessary for good approximation and vice versa. For example, the fact that P must be independent of mu was considered for a class of games to make the problem computationally tractable, but turns out it's also important for good approximation property. So it's possible that there's some kind of duality or connection between the two aspects. And as we said, mean-field games can be hard, but one important detail the computational complexity might miss is even if PPAD complete, MFGs can reduce the dimensionality of the original problem. Maybe in some cases, this completeness result doesn't really matter for applications. On the other hand side, an interesting orthogonal question of statistical complexity was not considered here, but here some results recently by my colleague Jiawei Huang have proposed some positive answers, suggesting that at least from a statistical perspective, mean-field games are not harder than single-agent RL. And finally, a future question that I would like to talk about, that I would like to analyze more, is that of oracle complexity. For example, the more realistic setting where we don't have a full computational description of the problem, but can only query, let's say, given a population, what the game dynamics and rewards look like. So in this case, it might be a realistic setting, and we might even come up with explicit lower bounds. So that is all on my side. If you have questions, I'm happy to elaborate more.
Thank you very much, Batu, for the very nice talk. Are there further questions? Okay, there is one question in the chat. How would you test this kind of asymmetry hypothesis in practice? Do you have any intuition on that?
So that's actually a very interesting question that I recently started experimenting on. I think there are many possibilities here in practice. I think it's a very interesting question that hasn't been considered in the past too much, is how can we, given an approximately symmetric game, how can we construct a mean-field game approximation? So how can we learn mean-field game representation itself? So I think different parameterizations, for example, somehow kind of neural network formulation could be beneficial, potentially kind of extend the applicability of mean field games even more. But in terms of statistical test or so, I don't have a good answer to that.
Okay, thanks. Other questions? So about the PPAD completeness for mean field game, you have for the lower bound parts. I imagine maybe you do that with explicit examples. I mean, you construct examples that have this property, I guess.
So in these free theorems, what we do is we show a polynomial time reduction back and forth to a problem that's known to be PPAD complete. For example, so one thing we can say for sure is that these problems are in PPAD at least, because they are some form of fixed point problems, which is usually used when, for example, establishing the existence of a mean field game mesh. But the fact that they're complete, we need to kind of do the reduction the other way around. What we do is, for example, I think I had it. So there's this certain PPAD complete problem that consists of finding a good assignment for so-called generalized circuit. So given a computational graph like this that might have recursions, that's not necessarily acyclic, we would like to find an assignment, arithmetic assignment that satisfies all operations like comparison, assignment, arithmetic linear combination, and so on. So we show that given any problem like this, we can construct a mean field game that amounts to solving this essentially. So this kind of backward reduction shows that the mean field game is also a difficult problem, like a hard problem.
Okay, thank you.
Thanks.
Can I ask a follow-up question? I think I might have missed this until a minute ago. So this results that you gave on PPAD completeness, these are even when P and R are pretty well behaved, right?
Yeah, exactly. So
okay, that's a big part of the punchline. This isn't for like, you know, badly behaved P and R that things go bad, but even for pretty nice ones.
Exactly, yeah. So these hold for just Lipschitz PNR, or like better said for simple PNR, which obey this kind of simple computational graph assumption. And even so for the finite horizon case, even with a certain linear reward structure, we can get PPAD completeness. Though I think in this case, we didn't rule out a pseudo polynomial time algorithm, but just show that PPAD completeness also.
Can you go to slide 15? Unless like if somebody else has a question, I can wait.
Sure. Which one?
Slide 15, I think.
15. Okay.
There was a comment here in the parentheses. Note the issue goes away if P does not depend on mu. And so that thing that you just said about the finite horizon H=2 case.
Yeah.
Can you comment on this parentheses versus the result you were just describing?
Yeah. So this is more on the approximation side. So if P doesn't depend on mu, the population dynamics are almost following like a regular Markov chain evolution. So of course there's the policy, but if we fix the policy, we can at least show that there's some non-expansiveness or even converge to some quick convergence to some stationary distribution. So if P doesn't depend on mu, from the approximation side, there's no exponential lower bound.
Oh, sorry. This was just about the exploitability.
Yeah, exactly.
I thought there was more of a connection. This is two sort of separate things.
Yeah.
Thank you.
And so on this side, so R still introduces some complications. So even if we're trying to compute like the mean field game Nash, dependence on R lets us reduce it to a normal form game actually. So it makes it difficult.
Okay, great. So if there are no further questions, thanks again, Batu, for the great talk, and thank you, everyone.